Hello everybody. Today we're going to be talking about stochastic differential equations and the zoo of diffusion processes that are often encountered in financial mathematics and physics. So, by the way, excuse the noise. I'm outside today. It was a nice day. But what we're going to first talk about is try to develop the notion first properly of a probability space and a filtration of a probability space. So let's say we have some triple, let's say omega, f, and p, where this is what we will define as a probability space. And omega is non-empty. It's a non-empty set of outcomes. And F is a sigma algebra, and let's write it as this. F is a sigma algebra on this sample space, and this particular sample space, a sample would be some realization or some realization that's random that we choose out of this sample space. Okay, and this sigma algebra basically defines this field axiom type of idea, if you will, for sets that are closed under complements and countable unions, kind of like the Kolmogorov axioms, if you've had any class in probability before. And the sample space is in the sigma algebra itself as well. And then the probability measure says if we take the filtration, it gives us a mapping between 0 and 1. This is a measure satisfying that the probability of the full sample space is 1, and that the probability of the null space, or of nothing happening, is 0. And then countable additivity just says that if we have some disjoint events in the sigma algebra, then we should have that the probability of the union of all of these events should be equivalent to the sum of the probabilities of those events. Okay? So that's the first way that we would that's the first notion that we'll describe as the notion of a probability space. Now what we need to do is talk about filtration. And it's important to do this before you ever touch stochastics, because we need to develop that a filtration, it's going to give us the baseline for the Ito integrability of a system, and allow us to talk about natural filtrations of a process itself. So filtration is just a family where we take an increasing sigma algebra with time, as time goes on to 0, or from 0 to some time later, of a sub-sigma algebra of the filtration, or of the sigma algebra, such that we'll take that this is a subset of the filtration through time, which is a subset of the full sigma algebra for all s is less than, for all s is less than t, which is basically s sandwiched between 0 and t, which also would be sandwiched between infinity. So we're assuming that it's finite. Technically, that should be a less than infinity. My bad. Now, what then this allows us to do is to define something called the natural filtration of a process of a process X. And what this is if we take the filtration through time of the natural filtration will just basically be denoted as sigma of X of S to be from 0 to S to T. Okay? Now, the usual conditions for a filtration is that it's first going to be right continuous. So, for something to be right continuous, that means I'm missing a U. For it to be right continuous, that basically means that the filtration should give us all of the intersections that if we were to take all of the S greater than T and take the intersections, that should give us the filtration itself. And it's also said to be complete, which means that it contains all of the P null sets. Alright, so that's what a filtration is. Now what we need to do is define what an adapted process is. Now, an adapted process is simply a stochastic process, S of t, or x t greater than 0, is said to be is adapted to a certain filtration if for every t greater than 0 the random variable x of t is measurable okay. So that means that for everything within some Borel sigma algebra, that we it takes some measure theory to define what a Borel sigma algebra is, but you basically have Borel functions or simple functions that then generalize to Borel functions and give you sigma fields. But what you would normally have is that you would take this random process here, and this the stuff that's adapted to this, if it basically it needs to be measurable within the filtration itself. Okay? And so then that allows us to say, well, because it's measurable, now what we need to do is describe integrability. So for because the whole point of measure theory is to construct spaces of integrable functions and define norms and all of these things over them. But you'll take that for some integral x and sub sigma algebra, let's say G that is a subset of F. In general, we can define something called the conditional expectation x g. So the expectation value of x given some g, that this is the unique almost surely. So it is unique almost surely, g measurable random variable such such that if we were to integrate over this particular chosen element of our Borel sigma algebra and integrate the random variable against this filtration or this sub-sigma algebra and integrate with against the probability measure, this should be equivalent to taking the function itself and integrating against the probability measure for all a within G. Now, properties of this are extremely important to note. Is that first we have linearity. So let's just go properties. Linearity just kind of looks like if I have some a x plus by given G, that we should be able to split up the expectation value itself and it obeys linearity. So that would be the first property. A second property would be something like it's called a tower property. So if we have some h as a subset of G, then we can take the expectation value of x given G given h to be equivalent to the expectation value of x given h. Alright, so that's another nice simplification. We also know that we can take out what is known. So if y is G measurable and it's bounded and satisfies some conditions, I think it's just measurable and bounded actually. The expectation value should be yx. It should be the product of both of those particular random variables, would then allow us to take out what we know. And take the expectation value of x against that G. And then finally, if we have that, if phi is convex, this would imply that the expectation value of a convex function of our random variable should be less than, or should be greater than or equal to the evaluation of the expectation value of that random variable given the G. Okay? So these are some nice types of properties that are interesting. And now we're going to define something that's very important as well, which is martingale. And so now, utilizing the tools that we have over here of adapted process, of expectation values, filtration, probability measure, we're going to synthesize all of this to define a specific type of adapted integrable process called, let's just call it M for martingale process. It's an adapted process, and it is martingale for all 0 to s to t if the expectation value of the martingale process given some adapted given that it's adapted, if it is equal almost surely to basically, as we take this projection of the conditional expectation value onto this filtered process, it should give us the sandwich subsigma algebra, or the index of that subsigma algebra for this particular expectation value. And what that basically means is that there's no it's kind of like a fair game. The best forecast itself of the future is what it is right now, or exactly what the time, or exactly what the value of the process is right now. Okay, that's an intuitive way to think about this. And then, of course, this naturally leads to the definitions of sub-martingales and of super martingales, which you could probably guess what they are. It would be where we take the expectation value to be greater than or equal to what it is currently, or we could take it less than same thing. Okay, and that would define what a sub-martingale is, and then this would be a super martingale. Okay, now we can define something called a stochastic process, and one of the basic, it makes a lot more sense to not just generally describe its stochastic process, but to do the most famous one, which is that if we were to take WT to be where t is greater than 0 on the probability space, so we're defining a new type of filtered process, and let's say is m-dimensional. Let's say that this initially is 0 almost surely, and that we have paths that give us parameterizations from t to w of t with elements of the random samples to be it's continuous. It's continuous on the sample space. They're continuous paths, almost surely as well. And we also have independent increments. So if we have, let's define some t0, t1, and partition all the way up to t in, the increments, let's say w of ti minus wti minus 1. These are independent. And then lastly, the increments themselves, if we were to take wt minus ws, they're going to be normally distributed in this way. And then assuming that we have an m-dimensional Brownian motion, we'll take the identity here for... Okay? So that's essentially what a Wiener, or what a standard Brownian motion is abstractly. Okay? It satisfies 4 of these types of things. And so we can develop, or we can think about something called Levi characterization. Now, what Levi characterization allows us to do is to then define a continuous local martingale. So let's say we have mt with m0 to be equivalent to 0, and to define some quadratic variation, say mi, mj, for these processes here to be equivalent to the delta ij of t, if this is what the quadratic variation is, or the quadratic variation process is defined essentially by if we took a Brownian motion and we wanted to take the limit as our increment goes to 0 of basically, let's say t sub I, and then minus w t sub I minus 1. The limit itself should be equivalent to time itself, almost surely. And what this quadratic, or what the Levi characterization allows us to do, is to ensure that whenever we see the quadratic variation scaling itself with as time goes on, is parameterized by this, and you can empirically Monte Carlo simulate this and observe that as we have a bunch of randomly sampled increments that sample from a normal distribution, as time goes on, the variance itself is spreading with time. And what's important is that Levi characterization gives you something called the Markov property. It's a Gaussian process with covariance of Ws and Wt to be equivalent to the minimum of S and T, so that would be the covariance. The paths are nowhere differentiable, almost surely, and they're also self-similar or fractal. So CWT given given some scaling factor, we can parameterize the scaling factor itself, its self-similarity, by this differential type of operator. Okay? So that's those are some of the important things to remember about Levi characterization, is they give us this fractal-like scaling of through time. Now we can move on to the Ito integral and the construction of Ito calculus. A process itself, let's say a process H is simple if there exists a partition from 0 to T0, T1, all the way to Tn equals T, such that H of T is the sum from I equals 0 to n minus 1 of Ht times the indicator function, which just tells you if you're in the support or not. Just tells you if you're in the support or not of the simple process itself, and each little H of T I right? This should be h of ti. Each little h of ti is going to be it's going to be ft measurable and bounded. Okay, and so that's how we would describe a partition. Oh my god, I can't spell partition. Okay. Now, for a simple function here, the Ito integral itself is going to be the integral as a function of these simple functions to be h of s, integrating against the process itself, dws, minus 1, and I'm running out of space here, but just continuing on over here. Times the increment here. Okay, so we're just summing over the simple functions with the increment, and that's what an Ito's integral is. That's all it is. It's like a it's a right-handed. The right-handed filtration kind of takes care of this, this basically this right-sided Riemann sums essentially, but instead they're like simple. It's a simple process that we then can define the integral as. So what a nice property about the Ito integral is the notion of isometry. And what isometry tells us is for a simple function h, we can have that the expectation value of the integral from 0 to t, h of s, dws. If we were to square it, that should be equivalent to the expectation value of this, basically taking the inside and squaring it. We get a nice isometry here. Okay? And that would take some time to prove. We don't really have time to do that right now, but that's just something important to ensure that you understand. Now, if we were to take a progressively measurable h, so let's take h with the expectation of an integral, saying it's square integrable, or in other words it's L2, the Ito integral is the L2 norm, or the L2 limit of simple approximations. So that's a very nice identity to walk through, but you can essentially say from 0 to t, integrating against the differential Wiener process, if we take the limit as n goes to infinity, we're then left with this particular limit where h of n are simple processes with the expectation being h of s minus h of s n squared ds going to 0, right? And so properties, this would have linearity, isometry. It also is a martingale, and Ito's integral is not pathwise. So those are things that you would want to understand as well. Now let's talk about the Ito process. the Ito process says, let's take a state and say we have some initial state plus the integral of some type of drift term and integrating over some random noise term. So we have a deterministic kind of term and then we have a random term. In differential form, the noisy, I guess, differential, I'm sorry, this should be a, if we were to take the differential of this random state through time, it would be noisy, but this is essentially the structure that we're working with before we choose to integrate through the S variables, okay? And so this is a drift that is adapted in L1, and then this is a diffusion that is adapted in L2. So basically that would just mean this is less than these are both finite integral functions. Okay, now what we can do is talk about Ito's formula in one dimensions now, because let's say let f be a continuous first differential function, second differential in space that defines some, or that parameterizes space of these rough types of curves. And X itself is an Ito process. Okay. What that means is that if we take the differential of the function, we can express this fully in terms of its deterministic partial derivatives. But since we're working with a random function, we have to add on an extra quadratic, or we have to add on a function that's differential with the quadratic variation itself. And so in order to prove this, you'd basically Taylor expand. So you'd want to take this function and add a plus dt, and take your random function and add a plus dx by dt, and subtract off from this the function itself to find the differential. And so what you would then do is say we want this to be equivalent to, you would basically just Taylor expand it out. So you'd have dx by, or del t by del x, del t times f dt plus del x f dx t plus 1/2. And of course, going on, like working through all of those terms, once you know that the differential of this squared should be equivalent to dt itself by quadratic variation, and dt itself is equivalent to 0, you can take that the of the quadratic variation with this random increment itself, or the differential of the Wiener process, or of the Brownian motion, we would get that dx squared should be equivalent to d sigma squared dt. Right? So that's essentially how you would want to do a little proof sketch of this particular form here of the Ito's formula for thinking about this. Now, if we wanted to extend this to multi-dimensions, it would basically be the same type of process, where if we say let x of t to be equivalent to x t1 to x of td, with dx ti. So we basically just make indices, and we would actually need to describe a diffusion type of tensor here. And for, again, first differentiable in space, first differentiable in time, second differential in space. This would be our time. This would be our, in d dimensions, space component. Then Ito's formula will become the differential as d by dt of f dt plus di for the space, or for the ith space component, plus 1/2 I comma j, and this would actually be a mixed partial derivative here, d the variation here itself. All right. So now that we have Ito calculus, we can talk about something called stratonovich calculus. So the stratonovich integral is going to be defined as the limit of a midpoint of Riemann sums. So if we take the integral from 0 to t of h of s, and we're going to denote the stratonovich integral with a little circle here. This is going to look different because it's as we take the partition itself to go to 0, this would be equivalent to the sum of n minus 1 to 0 of h t I plus h of these simple functions here divided by 2. But we're taking it in terms of the midpoint now. And what's nice about the what's nice about this is we can convert the stratonovich integral into an Ito conversion type of formula, and also the chain rule gets preserved in this one. But what happens is we have that the stratonovich integral can be expressed as the integral of the function itself plus 1/2 from 0 to t of f prime from s of t with the integrated with against the variation. And so for for dx is equal to the drift plus the noise, dw, we would get that f of x is equivalent to f of x dw plus 1/2 sigma f prime of x dt. And so that's a very nice property, is that we can convert from midpoints to the right-sided types of Ito integrals. Now, so let's say we have a function that's continuous and second differentiable. We would then have that the derivative or the differential of this would be equivalent to f prime of x at t, which is the normal chain rule in calculus. So that's essentially the rule that we can use from the stratonovich integral itself. Now, this allows us to formulate stochastic differential equations now. So keeping this in mind, a stochastic differential equation is simply just going to be something that looks like the form from 0 to t bx s integrated with respect to s. So we're just kind of generalizing this Ito drift formula with the diffusion. Okay? And the differential notation that we will use is to take this differential type of thing. Let's define everything. So this is essentially a state vector. A particular state that we're trying to model, right? A random state. B, usually for a stochastic process, we're working with this particular mapping onto the real numbers in d dimensions. And this is usually called a drift coefficient. Sigma is going to look like a mapping from this to the real numbers in d times m dimensions for diffusion. It's also a coefficient. And this is a standard the differential itself becomes the standard Brownian motion, or the differential of the standard Brownian motion itself. All right. And the diffusion matrix we can define for the special case that we don't have d of m in, or sorry, d times m. If we want to look at rd, let's say we have d by d, that special case, we can then define a matrix as the essentially as the type of quantity that we take a diffusion matrix and then multiply it by its transpose to give us this symmetric matrix that belongs to d by d dimensions. And so of course the ith and jth component of this can be expressed as this very simple tensor like contraction. Okay. So what we can do now is talk about existence and uniqueness of the differential equations. And how to do this. So this is basically what a stochastic differential equation is. It's just this form that we've encountered before. Now, let's talk about existence and uniqueness. We want to assume first that this process is Lipschitz. So that basically means that if we take some finite number, such that for all x and y, and the real numbers in d dimensions, and for t on the interval from 0 to t, that if we take if we were to evaluate this the size of this drift coefficient plus the norm of the diffusion coefficient, just basically doing the same thing, that should be less than or equal to some constant times x minus y. I'm not going to go through the proof of that. That's from ordinary differential equations, but or technically this is more than one variable, but that's essentially how you would try to prove something like that. And then for k, that's finite as well. We're going to impose linear growth, which just says that if we take the sum of both of their norms, that should be less than or equal to k of 1 plus the absolute value of x. Okay? And there should exist, if both of these things hold, right, then there exists a unique strong solution on this. By taking the supremum with the least upper bound on the expectation of the least upper bound on the square of the random variable. So basically kind of like on this pseudo second moment. And what you would do is basically do the Picard to proof this, to provide a proof for this particular unique strong solution. You'd want to provide Picard iteration, look that up in any good ordinary differential equations book, and then you'll use specific identity and Ito isometry. There's a bunch of different things that we've already covered that you would use the tools to prove such a thing, or prove strong or the uniqueness. But this is kind of an identity that I think would show up in the proof that might help, which is that if we were to take the n plus 1th segment and subtract off the nth, take the square of it, the supremum, this will always stay bounded by c to the m, some constant cm, to t to the n over n factorial. And this has to do with I think Grunwald's identity, and Grunwald's inequality, and it's like a bound on some binomial type of growth. So that's basically where it comes from like differentiating things. So anyways, that's where that comes from. Strong solution is basically just says that a process is defined on the given probability space, adapted to the filtration of the Brownian motion itself. A weak solution is a process defined on some probability space that's probably enlarged, and it's satisfying the stochastic differential equation itself. Okay, and there is another important theorem called the Yamada-Watanabe theorem that basically tells you that if you have pathwise uniqueness and weak existence, that then gives you a strong solution if you can prove the pathwise uniqueness and the weak existence of a solution. All right. Now, what we can move on to is the idea of the Kolmogorov equations. And the first thing that you would want to understand is what a generator is and what Markov property is. So, an Ito diffusion satisfies a Markov property for all bounded measurable functions themselves. So it just tells you that if you take the expectation, this should be equivalent to the expectation of the function. Almost surely. All right. So that's all the Markov property is this kind of, it has the property of being memoryless, and it only the conditional expectation is the expectation of the previous. Really, it only depends on the previous or the time now, basically. Okay. So again, it's like the best forecast of the future is like from the information that we have right now. Now, the infinitesimal generator. So let's say a generator, basically a quick example of this that's rough is that if we have some continuous function over the real numbers, the generator L is L acting on F, X and T, to be defined as some limit as H goes to 0, some function of F with F, H, T plus H taking the sequence of random functions that we have, or of the random input for the functions that we have here, and taking that limit as H divides that particular expectation. That gives us an infinitesimal type of generator, or I can define a generator here. Now the generator for diffusion, itself is going to look like dx plus t and bi dx. It's going to look very similar to what we had previously, but we're only taking the essential kind of structure without the differentials, and so we're just taking the generators themselves, where of course this I was previously what we had for sigma ik and sigma jk. Alright? And in coordinate form, the generator will actually basically the generator for diffusion will look something like nabla acting on F plus 1/2 the trace of A times some Hessian, or basically the convexity of that function. So this would be the generator itself for diffusion. Now the Kolmogorov backward equation, the forward equation is Fokker-Planck, but the backward equation will basically tell us that if we let u of t and x to be equivalent to the expectation value of this for a bounded measurable f, then u solves this particular equation here for t is greater than, or for t is less than capital T. And for u, substituting capital T in. And this has a nice Markov property, and basically when you take the derivative, you'd first want to start with the Markov property and something called Dynkin's formula. I don't think we went over Dynkin's formula, but you basically would do that and then take the derivative of it, and that would yield the PDE. And hence we can use just this diffusion generator itself to talk about the Kolmogorov backward equation. Now the Fokker-Planck equation is going to look slightly different, because what that does is it says, let us have some density of the random process, assuming that it exists. Then the derivative of the density should give us the dual of the generator acting on the basically the adjoint of the generator itself, of the diffusion generator. And what that looks like is the adjoint would give us Ij it would give us a nice kind of Fokker-Planckian type of evolution law, and the explicit Fokker-Planck will look something like this in coordinates, where we take nabla dotted with b rho plus 1/2 of basically the divergence, or sorry, the Laplacian, but we're taking the dot, the nabla dot a rho here. And this would imply, of course, that we'd have the derivative. If we take the derivative of the density integrated over all of space, that should be equivalent to 0, because we don't want to violate the Kolmogorov axioms or probability, or we don't want to violate the fact that we have an abstract kind of sigma field. So we don't want any violation of probability, right? I mean, we need to ensure that probability itself is conserved, that probability mass is conserved, and that is true since the integral of the adjoint of this acting on rho dx should be equivalent to 0. And you would have to do like an integration by parts with some boundary terms vanishing, all of these things. But that's how you would get that. Now let's talk about the classical diffusion processes. Now that we have the Kolmogorov, we have the Fokker-Planckian types of development that's happened here. I mean, this is just for a rough picture, but the SDE. So let's first start off with this with the brownian motion. All right, so brownian motion with drift would just look something like dx times drift mu with a random term, and brownian motion for x is equal to little x0. And the solution to this, the generator, obviously, the generator itself would look something like 1/2 sigma squared d sub x, or basically the second derivative, or sorry, second derivative, second partial with respect to x. Okay. And what the Brownian motion with drift is it actually literally is the Fokker-Planck equation, and the solution is just done by Fourier transforming to give you the particular distribution itself as a function of time, which is literally 2 pi sigma squared t times the exponent of x minus x naught minus mu t squared over 2 sigma squared t. Alright? Minus. That is the solution. So this particular differential equation is solved already. Now we can study geometric Brownian motion as well, which geometric Brownian motion is very related to finance. So we'll just kind of basically you add in the random term within here, and if you apply Ito's formula to f of s times log of s, and this gives you the differential of log s to be equivalent to 1 over s. It's basically just logarithmic coordinate choice. This will give you 1/2 squared mu plus this. Okay. Which is after substituting in and simplifying this out, you would therefore get that the solution to this would actually be mu squared plus 1. It would look something like this, which is very easy to simulate and everything. The moments are analytical. Pretty much everything about this is analytical, and we don't really have to spend too much more time on this. There's also another type of process. So this is a geometric Brownian motion. There's another type of process called the Ornstein-Eulenbeck process, or the OU process. And the Ornstein-Eulenbeck basically is this type of process here. Which looks like that, and we have like a mean reversion. Okay, so you can think about this as a mean reversion strength. This is like a long-term mean, and this is more like a volatility. Okay? And there's not really too much interesting about this. You solve it by like with integrating factor methods and then, you know, integrating it out. But the distribution is also, the stationary distribution is literally normally distributed. But it does have say what, I'll just show you the closed form formula. I don't feel like deriving it right now. Sorry. But yeah, I mean, this is the Ornstein-Uhlenbeck process. It's basically Gaussian with like a, you know, the stationary distribution is completely a normal distribution in terms of these parameters here, sigma and kappa and theta. Okay. But basically, it's kind of like a process that if it starts off somewhere and there's like a mean, it starts off here, it's going to go down, and then it's going to like want a mean revert around this type of thing. So it eventually settles. It's ergodic, in other words. Okay. The Cox-Ingersoll-Ross process, or the CIR. This is used for like interest rates and stuff. But basically, you'll have something pretty similar. You'll have that same long-term mean, but instead, this is a variable itself. Oh no, this is the same. Sorry. It's a square root of the volatility itself. It plays a factor into this, the adaptation on the Brownian motion. And so we'll have that, okay, 0, this is mean reversion again. This is long-term mean. And this is the volatility of volatility. The volatility of volatility. And this one actually has an interesting solution structure because it has a marginal distribution that's this like non-central chi-squared. So the actual solution itself will look something like, analytically, it will look like 1/2 of 1 minus kappa t over 4 kappa times a chi-squared type of distribution, which if you didn't know, a chi-squared is a special case of the gamma distribution, which has 2 arguments. But our arguments here are going to be these types of coefficients, or these types of parameterizations. All right. So that would be the chi-squared distribution. Chi-squared is like, basically it has some degrees of freedom and some non-centrality. But yeah, and so these would have nice analytical moments, everything that makes it an interesting type of process. So yeah, and then the last one would be the Heston stochastic volatility model. This one actually just kind of mixes everything. It couples this volatility of volatility and there you actually have to have 2 different probability measures as well, for the volatility itself, and then the so you're adapting with respect to the some kind of price process. The financial mathematics becomes synonymous here with this type of with these types of systems. So I'm just like talking about it as if it's price. But yeah, and then dV, the volatility here, would be basically the Cox-Ingersoll-Ross. I'm sorry, this should be minus dt plus so basically this guy here goes into this particular model and it's coupled, and they have their own they're their own type of processes, but you basically impose this type of correlation structure here, or of course your correlation coefficient would be 1, or would be less than 1, and you would also have a diffusion matrix that looks a little more complicated. Half rho squared. And the diffusion tensor, if you were to take the diffusion, if you take this and then take its trace, multiply them together, as we constructed earlier, this would give us v squared. It's a nice it's symmetric in its trace, which is nice. But yeah, that's kind of the and this should be, let's see, yeah, okay. But yeah, that's kind of what we would have here, and you can also define Malevin covariance as well. We'll talk about it maybe another day. But the last stochastic process that I want to talk about is Langevin dynamics. Now, Langevin dynamics, the overdamped, we're going to work in physical coordinates now. But this type of process here takes our gradient of a potential that is a function of a random process plus 1 over the square root of 2, or sorry, square root of 2 over beta dwt. And of course, this is a potential that maps some d dimensions to the regular real numbers. It's potential, oh my god. Potential energy. And beta is 0. This gives us inverse temperature. And the generator, of course, just looking at it, you could probably guess that it would be the gradient of this potential dotted with nabla plus 1/2 beta over the Laplacian. And the stationary distribution, what's interesting about this particular process that you should understand is that the stationary distribution happens to be at p infinity of x. This happens to be a Maxwell-Boltzmann type of distribution, which we spent a very long time talking about in our probability video. But yeah, so that's kind of a nice recovery of the stationary distribution. And then also Fokker-Planckian, the Fokker-Planck equation would look a lot more like what we're used to seeing in physics and statistical mechanics. Which is very nice. And so that's essentially what would define the Langevin. The Langevin dynamics. Okay. Lastly, what we'll talk about is jump processes. So jump processes, we can start with the Poisson process that looks like, let's say, in 0 with intensity. First of all, we would start off with the population of 0, and the increments themselves. So this process basically, it's the process of rare events, right? What is the probability of, like, you know, something happening like in this instant or whatever, and just like an excitation type of thing, not self-excitation, but just a type of excitation. Dependent increments, and it's continuous through time, but it just kind of like the increments themselves have a probability of happening or not happening. And 3. For 0. So some properties of the Poisson process, which are nice, is that its probability for n of t being equal to k, this should be kind of a regular Poisson type of distribution, but you just have it as a function of time here. So we're just kind of putting the time variable into there, and the expectation value of our Poisson process is equivalent to lambda t, and the variance also is equivalent to lambda t, just like the regular Poisson process, just like the regular Poisson distribution. You just kind of have the time scaling there, all right? And jump times, basically, so let's say we have some times where we get some jumps to dot and ti minus t1. These are exponentially distributed. Okay? And the generator itself for the Poisson process is not completely obvious, but it's just going to look like the intensity times the intensity of the Poisson process times basically an increment, or a difference between an increment of the function itself. Okay, so it'll just kind of look like this, and then like bop, and wait some time. It's random, right? So bop, maybe bop, something like that, and that would be the value of the Poisson distribution, how it would look. Okay, intuitively. Now we can also move on to a compound Poisson process. Just note that what it would do is basically add on multiple Poisson processes and how they stack up. And you would need a characteristic function to define its moments and all of these things. But I think we can move on to the Levi process now. And hold on. Oh, need a break. Okay, so the Levi process. It's basically a process with stationary independent increments and something called stationary So we're keeping that independent increments, but there's something called CAD lag paths. Okay. And CAD lag paths they're messier paths. So just like a normal Brownian motion would look probably something like this, right? Whereas CAD lag paths would look something like that. Okay. If that makes sense. So basically they have kind of a more geometric, these paths have more of a geometric type of area that gets filled up between them and like the angle that they traverse, and so yeah, versus a regular Brownian motion. So that's the intuitive way to look at it. You can open up any math textbook as well. There'll be definitions for that. But the process itself is just defined as the expectation value, some IU, so T, being exponentially distributed for some psi of U, where psi of U is EB dot U minus 1/2 T sigma, the covariance, plus integral of R D quotiented out by the null set U dot X minus 1 minus IU dot X indicator function of X V dx. Alright? And this can be reduced to something called a Levi triplet. Alright? And this should be this is a nu. Let's do nu like this. Let's write nu like this, because that looks like a gamma. Okay. And so that would be the Levi measure satisfying, well, first of all, this would be a drift, right? And then this would be a nice Gaussian covariance type of term. And this guy is the Levi measure, by taking the minimum of 1 dotted with the squared of the magnitude of x x here. Boom. Alright. And I'm not going to write out the generator for this one, but you can look it up if you want. But it's basically, this formula here is called the Levi. Just if you want to look this up, it's called the Levi Khinchin formula. And the Levi Khinchin formula just gives us, that's what this, right? Khinchin. Yes. It just gives us the general way to describe Levi processes. And then, of course, you would have jump diffusion SDEs that give you even more kind of that. Basically, the Levi. I think the Levi processes are enough to motivate jump diffusion SDEs, but you can generalize them further. But yeah, that's pretty much everything that I wanted to go over today. We can talk more about maybe possibly Malevin calculus in future videos, or the Gersinoff's theorem measure change. I just don't think like that's super important right now, just for the sake of getting all of these types of stochastic models out of the way. But yeah, hopefully you guys enjoyed this, and it made some sense, and let me know what kinds of things you guys want to see from this channel as well. Join the Discord, join the crazy debates that we have in there, and yeah. All right, thank you guys for watching.